regression. That's a term you've just met in the unit. And this program is going to look at the history of the idea, and in particular, where its name came from. At the beginning of this century, the statistician Carl Pearson collected a large amount of data based on measurements made in human families. One set of data is represented by this model. It shows the heights of a large number of fathers together with the heights of their adult sons. 1,078 measurements in all. In other words, we have 1,078 measurements of the heights of father-son pairs. Fathers' heights are plotted along this axis, and their sons' heights along this one. And the height of any one block is proportional to the number of observations contained within this square. So, if we take a father's height of, say, 66 inches, and a son's height of 63 inches, I can read up and across to this column, which has height proportional to the number of cases Pearson found with fathers of this height and sons of this height. In fact, the measurements were all rounded to the nearest inch. Now, because we're looking at two random variables, we call this a bivariate frequency distribution. Looking at this model, we can detect some general features. The observations in the far region correspond to fathers and sons' heights that are both large, because tall fathers tend to have tall sons. Whereas the observations down here correspond to fathers and sons' heights that are both small. Short fathers have short sons. But that's no great surprise. You can see that the most common observations are around here, in the middle of the model. Now, the overall shape of this model suggests that it might be reasonable to assume the observations are drawn from a bivariate normal distribution. Let's have a look at that. Here we are. This is a three-dimensional model of a bivariate normal probability density function, with father's height measured along the x-axis and son's height along the y-axis. And clearly, it has a similar shape to the data we've been looking at. You've met some of the properties of this distribution in the unit. We're going to explore some of them again now. First of all, what do the marginal distributions look like? Unfortunately, it's not easy to see these on the theoretical model. So let's go back to the data. I can find the marginal frequency distribution of the father's height by summing the blocks in this way. All the observations measured by Pearson with father's height of 59 inches, to the nearest inch, can be found in this column. If we add these blocks together, we obtain the total frequency for fathers of 59 inches. I'll put these blocks here in the margin, and that's why the resulting frequency distribution is called a marginal distribution. Now I'll do the same thing for fathers of height 60 inches. In this way, I could go on to build up the complete marginal frequency distribution of fathers' heights. And this would give the distribution of fathers' heights in Pearson's data, irrespective of their sons' heights. And then if I were to start again and sum the blocks row by row, I would build up the marginal frequency distribution of the sons' heights. In fact, we've already done this, and Gillian has the results.
Here's the complete marginal distribution of the father's heights. I had to scale it down somewhat to fit it on this board. But looking at this, you can see that apart from a few fluctuations here, it has the shape you'd expect for data from a normal distribution. But let's compare it with the marginal distribution of x, which we'd get by integration if the theoretical model is the one we've assumed it to be, namely bivariate normal. Here it is, drawn to the same scale, and indeed it is a normal distribution. Clearly they look alike. Now we'll look at the marginal distribution of sun's heights. Here we are. It has the same general shape as the one we've just seen. Again, we'll compare it with the marginal distribution of y from the bivariate normal PDF. This is also a normal distribution, and you can see that they agree very well. Now, before we leave these diagrams, there's one important feature I'd like to point out concerning these distributions. For the data, the variances of father's heights and son's heights are equal. Consequently, the theoretical model we're assuming also has equal variances. That is, the variances of the marginal distributions are equal. And if I place one of these curves on top of the other, they do fit exactly. Well, we've looked at the marginal distributions, but there's another univariate distribution we can derive from the bivariate distribution, namely the conditional distribution.
If I slice this model at any value of father's height, we can see in cross-section a frequency distribution of son's height. What is this distribution? Well, it's the distribution of son's height given the particular value of father's height at which this cross-section occurs, in this case 70 inches. And so it's called the conditional distribution of son's height given the father's height is 70 inches. Moreover, there's a conditional distribution of son's height for every father's height. And similarly, a conditional distribution of father's height for every son's height. What's the equivalent on the theoretical model? What you're looking at here is the conditional PDF of y given x equals 70. It's a normal distribution. So if this is a reasonable model for the data, the height of a sun chosen at random from all suns with fathers 70 inches tall will have this normal distribution. This may not have been very convincing from the empirical data model, but then there aren't too many observations in the column corresponding to 70 inches. The question we're now going to consider is, what is the mean of this conditional distribution? Well, for x equals 70, the mean of the conditional distribution of y is just under 70. But what is it in general? What's the conditional mean of y given x equals some value little x? We could answer this by slicing the model up at a number of places and looking at the conditional distributions we find. Let's see what happens when we do this. Here's our bivariate normal distribution. If we open it up, we can see again the normal form of the conditional distribution of y given x, and we can mark the conditional mean on the top surface. For small values of x, the conditional mean of y is small. We'll now put in the conditional mean of y for a range of values of x. For larger values of x, the conditional means are larger. Now, if we turn the distribution, we can see that the line joining the conditional means is a straight line. This line is called a regression line because the conditional mean of y given x is called the regression of y on x. We got this regression line by looking at a series of conditional means of this bivariate normal distribution. In view of the relationship we've seen between the empirical model and the theoretical model, might we not expect to find that plots of the corresponding means for Pearson's data lie approximately on a straight line? Let's see if that's true.
For each father's height, I've plotted the average of their son's height. For instance, for fathers of height 70 inches, the average height of their sons is just below 70 inches. And for fathers of height 64 inches, the average height of their sons is just below 67 inches. Now you can see that all these averages lie approximately on a straight line, giving us further evidence that the bivariate normal distribution is in fact a reasonable model for this data. So let's put a line through these averages. And we get an estimated regression line. We noticed earlier that a tall father tends to have a tall son, and that a short father tends to have a short son. This is, of course, shown by the fact that the regression line has a positive slope. But another interesting point to notice is that although tall fathers do have tall sons, the height of the son is on average smaller than the height of his father. For instance, for fathers 75 inches tall, the average height of their sons is 72.5 inches. The same sort of thing happens with short fathers. Their sons, on average, are not as short as themselves. For fathers 60 inches tall, the average height of their sons is about 65 inches. The orange line drawn on this graph is the 45-degree line. In other words, it has slope 1. The regression line, therefore, has slope less than 1, and this explains the phenomenon I've just been describing. On average, tall fathers have sons less tall than themselves, and short fathers have sons less short than themselves. It was data similar to that collected by Pearson, although on a smaller scale, that led Sir Francis Galton in the 1880s to the idea of regression. Galton, as well as being an explorer and pioneer of the use of fingerprints for identification, was an anthropologist. He had a predilection for measurement and quantification of human faculties, and in the course of his researches noticed the phenomenon you've just seen. Galton called this effect of tall fathers having not so tall sons and short fathers having not so short sons regression back towards the population mean, or as he put it, toward the mediocre. He based this conclusion on graphs just like these. So the name regression springs from one particular set of investigations, but the name has stuck. The term regression is now used to mean the expectation of y given x, which, if the distribution of x and y is bivariate normal, is, as we have seen, a straight line. Before the programme, you showed that when x and y have equal means and equal variances, the regression of y on x can be written in either of these two ways. In this particular case, rho, the correlation, is the slope of the regression line, and we saw that this was positive for Pearson's data. Now, for a father whose height is greater than the population mean, x is greater than mu. So x minus mu is positive, and rho times x minus mu is positive, and the whole expression is greater than mu. So we'd expect his son to be taller than average as well. Now let's look at the second expression. We know from earlier in the unit that the correlation rho cannot be greater than 1, so 1 minus rho is positive. And this is positive. So the whole expression is smaller than x. In other words, we'd expect a son's height to be smaller than his father's. The two expressions taken together show that on average a son's height is closer to the population mean than his father's height. In a similar way, if we consider a father of below average height, we can show that we would expect his son's height to be closer to the population mean than his.
Perhaps this is a good point to mention that for the data collected by Carl Pearson, the mean son's height is actually an inch greater than the mean father's height. The mean father's height is 67.7 inches, and the mean son's height 68.7 inches. To make things easy, we ignored this in our discussion of the regression equations. But even if we did take it into account, we would find no material difference in the result, as the regression back to the population mean is so strong compared with this increase in height from one generation to the next. Well, we've now spent some time investigating the regression of sons' height on fathers. In other words, of y on x. Now we're going to reverse the procedure. If we know the height of a son, what would we expect his father's height to be?
You might think that we could find the expected father's height by reading back on this graph for the given son's height. However, each point on this graph is a plot of the average son's height for a given father's height. What we need to do is to go back to the original data and draw up a graph of average father's heights for given son's heights. The resulting graph looks like this. As before, father's heights are along the x-axis, son's heights along the y-axis. For each son's height, we've plotted the average father's height. Again, you can see that these averages lie approximately on a straight line. So once again, I'll put a straight line through them. This is our estimated regression line of father's heights on sons, that is, of x on y. Now, do we get regression back towards the population mean in this case too? Let's see. For tall sons, say 75 inches, the average height of fathers is about 71 inches. That's much closer to the population mean. And for short sons, say 62 inches, the average height of their fathers is about 64 inches. Again, much closer to the population mean. So we do indeed get regression back towards the population mean. The orange line is again the 45-degree line. But don't be deceived into thinking that the regression has slope greater than 1. Remember, we've left the axes as before, so that father's height is measured along the x-axis and son's height along the y-axis. But normally we'd plot the expected value of x given y against y with these axes interchanged, so that the whole graph would flip over, giving a picture not unlike the first one.
This model is of one particular bivariate normal distribution. It's the one from which the data might reasonably well be drawn. The variances of x and y are equal, and the correlation coefficient ρ is about 0.51. Galton and Pearson, among others, also looked at other pairs of random variables with equal variances, but with different values of ρ. In other words, with regression lines with different slopes. Let's see graphically what happens to this distribution as ρ varies. Here's our bivariate normal distribution with the regression line of y on x marked in. In this case, ρ is 0.51. Let's see what happens to the distribution as we change the value of ρ. As ρ increases, the distribution gradually becomes more and more concentrated about the regression line, until finally, when ρ is 1, the distribution is confined to the regression line itself, so that the value of y is completely determined by the value of x. Now as we decrease ρ, the distribution becomes less concentrated about the regression line. And when ρ is 0, the distribution has this symmetric shape. As ρ decreases further, now through negative values, the distribution again becomes more concentrated about the regression line, until finally, when ρ is -1, the distribution is again restricted to the regression line itself, so that once more, for any particular value of x, the value of y is completely determined. Now let's look at the conditional distributions for our bivariate normal distribution. We'll begin by looking at the conditional distribution of y at the mean value of x. To do this, we'll take a vertical section of the bivariate distribution through the mean and scale the section to give the PDF of the conditional distribution. Let's do this for other values of x. you can see the conditional means are on a straight line, and that the conditional variances are all the same. Now let's change rho. For this value of rho, the conditional variances are again the same for every value of x. And this is true for any particular value of rho we choose to take.
You've seen the effect on the bivariate normal distribution of changing the correlation coefficient rho, but with the variances equal. Now we'll see what happens if the variances are not equal. This was a situation which, in fact, Galton encountered in some of his investigations. For instance, when he looked at the relation between human height and foot size, two variables that obviously don't have the same variance. Let's see graphically how the distribution behaves in this case. Once again, here's our bivariate normal distribution with rho equal to 0.51 and equal variances. Here's the regression line of y on x, and also the orange 45-degree line. First, we'll reduce rho to 0. Now let's see what happens as we increase the variance of y. The distribution is being stretched out along the y-axis. This is what it looks like when the variance of y is 4 times the variance of x. Here's the 45-degree line again, and as we increase rho, the slope of the regression line increases, until in this case the two lines coincide when rho is 0.5. And as we increase rho further, the slope of the regression line becomes greater than 1. So, when the variances of x and y are not equal, the slope of the regression line can be greater than 1. So what have we seen in this program? We've looked at 1,000 or more observations from a bivariate frequency distribution that can be reasonably modelled by a bivariate normal distribution. We've seen that both the marginal distributions and the conditional distributions are normal. Moreover, the expected value of y given x, that's the regression of y on x, gives a straight line when plotted against x. We've also seen that this name, regression, derives from similar work carried out by Galton on data like this. It turns out that the bivariate normal distribution is an excellent model in many practical situations. So this simple regression relationship, a straight line, is a fortuitous and above all convenient result.